Everyone speak. Sweet. So fine tuning. So it's become apparent to me that a chunk of the lab is shifting gears, and even if they don't have a coding background, generative AI models are becoming very big in the lab. So I thought it might be useful for me to do a quick discussion on fine tuning, kind of going over what is fine tuning, what are generative AI models. So just kind of setting up that foundation, the types of fine tuning that are available, what you need, data sets, and then kind of wrapping it up with what happens during fine tuning as a whole to like really dive deep and make sure everyone understands what's happening. And then ending it off with use cases, evaluation, and common issues that may be brought up. So, what is fine tuning? If you look up the definition in the English dictionary, you'll see to make very small changes to something in order to make it work as well as possible, right? So, almost like revising something, right? So try to do small changes until something's the best it can possibly be, which makes sense, right? You might fine tune a presentation if you have one coming up, a speech. If you're a student, you'll probably revise or fine tune an essay before submission, right? To try and guarantee the best marks you can possibly get. So if you were to create an analogy with this, one thing you can think of is a raw diamond, right? You have to do a lot of processes, a lot of step-by-step changes in order to take the raw rock form of diamond in order to make it something shiny that you'll see in a necklace, a ring, whatever it might be. And the same definition holds true when it comes to machine learning. It's a process of adapting a pre-trained model for specific tasks or use cases, right? So in this case, the rock, right, the raw form could be something like GPT-3, a general, pretty well-rounded large language model. But then you take the step and you train it and have it learn to become the conversational agent that we all T3.5 Turbo, right? So the idea is leveraging something that's already there, something already has knowledge, but then tweaking it so you can use it for a specific task or a use case, right? So that's the idea of fine tuning. You know what fine tuning is. It's the notion of making these step-by-step changes and helping something learn, right? So in order to understand a little bit better, we kind of need to go over generative AI models, which are models that take inputs such as text, image, audio, video code, and generate any new content in these modalities, right? So text to image, text to text, image to video, wherever it might be. There's so many out there now that I've pretty much lost count. The one most of you are familiar with is large language models, so LLMs, so text to text, ChatGPT, Claude, Llama, etc. You can use it for a number of reasons. In our case, we've been using it for the ChemFront project to do extraction from research articles. But it can be as simple as rewriting an email, which I've seen a number of you do on the Wishart Lab OpenAI account when requesting for days off. Stable diffusion is another one that I've been able to work with in the past, and that's text to image. So similar to DALL-E, you put in a prompt and it generates an image for you. You could use this for drawing logos, or maybe if you're an artist and you need some type of inspiration for a new project, put it in the prompt and see what SD gives back to you. What's worth noting about generative AI models is their architecture, right? So the architecture of these models is pretty much blocks of different code or functionality that are stringed together to create the model that we have. So you take an input, you pass it through one block, it gives you an output, and that's now your input to the next block. And this chain continues on until you get to the end. This is a very linear example, and it can definitely branch out into a number of nodes, right? So it can get very complex very quick. But it's worth noting that architectures are going to vary from model to model. So if you give one prompt to ChatGPT and then the same one to Llama, chances are you're going to get a very different output, right? And that's has to do with these architectures, or at least part of it. So these architectures can kind of be seen as like the human body, right? They're the outer casing. Um, so here's Llama, here's Mistral. They look very much similar, but if you look at the table below, there's additional enhancements and innovations and mechanisms, different attention mechanisms, and Mistral uses it, Llama doesn't. So although they look similar, they're still different. And stable diffusion is completely different from large language models. This has a unit architecture, it works in the latent space, there's time steps associated, we're using cross attentions, not self attentions. So quite a bit different. These architectures are going to vary for their specific use case. But like I said, this is the human body, right? It's kind of like the skeleton, but the real intelligence for these models comes from their weights. And these weights are pretty much just numbers. They're vectors, they're matrices. that the model learns and adjusts during its training phase, right? So it's pretty much the model's brain. This is where all the information comes from. And each weight represents a specific relationship or understanding that the model has captured from the data that it was trained on. When looking at architectures, we see that there's a number of layers, right? Each of these layers can typically be associated with a weight. The attentions probably have more weights like QKV weights, right? So every part of the model, every part of the architecture has some knowledge that helps it get the output that you see, right? So similar to how we as humans learn from examples and experiences, the model is going to learn from the data that's being trained on. And we're fine tuning. So fine tuning starts with the pre-trained weights. There's already numbers there. So what's really happening during the whole fine tuning process is for each of these weights and all these numbers, we're kind of just moving a slider a little bit left and right to adjust the numbers to best encapsulate the additional information it's now seeing through the training data. And this as a whole is the fine tuning process. Start with some already present numbers, move the sliders a little bit to help the model encapsulate the new information that is seeing. That is fine tuning in a nutshell, right? So we know what fine tuning is, we know what it does. What types of fine tuning are available to us? Well, there's a number, but two supervised techniques that I'll go over are full fine tuning and low rank adaptation or LoRa fine tuning. Full fine tuning is going to adjust all the weights slash matrices in the model, right? So if your model is this big and you're changing all of these numbers along the whole architecture, you can kind of imagine how computationally expensive this is going to be. And you're changing everything. So your output weights, right? The files you're going to be saving are going to be like hundreds of gigabytes. It's going to take up a lot of space, but you're able to teach the model in every part of its structure. LoRa fine-tuning is nice because it's a type of parameter-efficient fine-tuning that only updates a small part of the model weights and specifically targets those that have the most significant impact on the task at hand, right? So let's say you want to fine-tune stable diffusion text to image to generate Disney-style images, or let's say Disney-style characters to be specific. What are some common features you might see? You probably see like big smile, big eyes, right? Big expressions, big cheeks, whatever it might be. It could be the case that from the entire model, only like the beginning chunk is responsible for creating these features. So it doesn't make sense to train everything else. Just train this one section. And now we only have a small set of weights that we need, and we can still leverage the rest of the pre-trained information that's there. So for this reason, it's a lot more efficient and you're going to get those lower weight sizes. This might seem a little fuzzy, so I'll explain it one more time. Imagine the blue nodes here are different layers within the model and all the lines represent the weights. In the full fine tuning, you're changing everything, right? You're going to alter the weight sliders for all the weights there on the model. While for LoRa fine tuning, you can see that the lines are a little bit thicker here, and that's because they're frozen. We're not changing these weights at all. What LoRa does is creates its own set of weights. So these little gray lines in the back, and only for a specific section. So we have the pre-trained weights, and then LoRa creates its own adapter weights that you can add on top of the already trained information that is there. Nonetheless, regardless of the training type that you're using, you need data sets. And there's pretty much three different types of data sets you need: training, validation, and testing. Training is pretty self-explanatory. It's what the model is actually going to be trained on. So it's a set of data from which the model is going to learn the hidden features or patterns. So with stable diffusion and Disney images, like the big cheeks, big eyes, things like that. But you need to be able to test and see how well does a model perform on something it hasn't seen before. If I keep telling you over and over and over again, the red plus blue is equal to purple, and I ask you that a year later, and I tell you that every day, you'll be able to spit back the same information. So that hasn't told me that you've learned anything about color combinations. So by creating testing data, something that the model hasn't seen before, I can now ask you what is red and yellow. And if you're able to tell me that's orange, then I realize, okay, you've understood like the core concept of color combinations, and you're able to spit back information that you haven't seen before. So you're able to actually do the logical thinking needed there. So the testing set we'll use after training is to complete to see, okay, can the model actually do this on its own and on something that it hasn't seen before? The validation set is very similar to the testing set, except we're not going to wait for training to finish. Rather, every iteration or every, so often, we'll test the model and see, okay, is it still capable of, processing and doing things on things it hasn't seen before? And this will make more sense as we go on. But it's just there to validate that the model's actually learning. And you'll hear later on is to make sure that it's not getting overfit on just the information it knows. So to kind of like hammer this in one more time, if this top rectangle here on the left is the training pipeline, we'll train the model and then evaluate it on the validation set, make any tweaks necessary, go back to training, evaluate on validation, and continue this cycle until we're happy with the validation number that we get. And then finally, we'll confirm the results on the test set. A question that I've already heard asked is how do we go about splitting the data that we have? Well, if you look at typical machine learning papers or the machine learning community, these are some go-to ratios, 80, 10, 10, 70, 15, 15, 60, 20, 20. The main importance here is you need to make sure that your data is random. So if you have 1,000 samples of data that you can use, make sure the order is randomized, and then you can say, okay, make the first 80% training, the next 10 testing, and the last 10 validation. It could be the case that there's things that are up here that are not down there. So you need to make sure everything's randomized in order for all the data to be spread out. So the content in all the different sets is going to be different, but the structure still needs to be the same. And the structure of the data is going to depend on the type of format you have. One thing that they all have in common is input-output pairs, what the model should be able to take in and what it should give back if it's optimal, right? So if you have a question and answer task, you'll probably give it a question as an input, and your output's going to be the answer to that question. If it's sentence completion, your input's going to be like a part of the sentence, your output's the full sentence. Extraction, like in our case, input's the research article, and your output is all the extracted information. Some models will have a prompt template that they recommend you use when it comes to fine-tuning. And the idea here is the template was designed in a sense to help the model learn as best as it possibly can from your data set. And the data sets are also going to vary depending on the type of generative AI model you're using. For LLMs, everything's going to be text, so like an input plus instruction, and then your output, everything's text here. Whilst for stable diffusion, you have prompt inputs and image outputs. So at this point, you know what fine-tuning is, you know what generative AI models are, you know what's happening in the background of fine-tuning, you know what you need to fine-tune, but just to make sure that everyone has a pretty good idea of what's happening here, we're going to pretty much walk through the whole fine-tuning process and see, okay, where are the weight changes actually coming from? So you know why everything here is very important. And that can be described by this one image, broken down into two parts, the forward pass and the backward pass. And we're going to kind of break it into different sections here. First part is the data feeding, the input. This is the batch of training data that's going to be fed into the model, right? So let's say you have 100 samples of training data. The first hyperparameter you're going to want to pick out is the batch. How many of these samples should we pass in per iteration? And one iteration is a pass through the whole model. So if you have 100 samples and your batch size is 20, that means it's going to take you 5 iterations for the entire 100 samples to go through the model. And once all samples have gone through the model at least once, we call that an epoch, which is another hyperparameter. You can determine how many epochs you want your model to be trained for. But once we pass in the batch of data, it's going to begin the forward pass. Remember, these models are already pre-trained, so there's already weights there, so there's already some intelligence there. It's going to go through the model and give us back an output. But the data set also has an output, the ground truth output, what the model should be able to predict given the input we provided. So we can compare the output to the actual output and kind of create a loss, right? This is essentially telling us and comparing the model's predictions to the true labels or desired output and a measure of how well the model's predictions align with the target value. Based off the loss, we can do some gradients, some derivatives. It gets really math heavy. We're going to skip all the math, but you compute some gradients, and then you can begin the backward pass. The idea of back propagation, where we're going to update the weights in the model based off the gradients we calculated over some optimization algorithm. Because the goal is that over the fine-tuning process, we want the loss to get lower and lower, because that tells us, okay, the model's producing outputs that are closer to the desired output. And once all the data has gone through the model, we've now completed an epoch, and you can repeat this for however many times you like. Now you might be wondering, okay, I understand what fine-tuning is. You drilled it into our heads enough time, but what are the actual use cases when it comes to fine-tuning? And in one case is what I want to fine-tune. And you can break it down into a number of reasons. I'm going to break it down into two main ones. The first one being customizing styles and specialization. So we touched upon this when I gave you the Stable Diffusion example, right? Tailoring the model to generate images in a specific style. We picked Disney, so you can do some LoRa fine-tuning and have the model generate all these Disney-style cartoons. But for LMs, you can do the same thing. You can adjust the model to produce text in particular style for or a specific task. If you're looking in the style example, let's say you have a chatbot and for whatever reason you want to talk like Shakespeare, you can go ahead and create a data set of Shakespearean text, fine-tune the model, and there you go. You got a chatbot that talks to you like Shakespeare, right? If you're looking at the task side of things, this is something that we did with text extraction, kind of helping the model to just get really good at information extraction. So giving it inputs of articles and having it give back list of different chemicals or relationships that we're interested in. If you want to create something for code generation, your input's going to be some type of problem and your output's going to be the code it should generate. The idea is just fine-tuning with relevant data to help the model learn the nuances and specifics of the task that you're interested in. The other one is domain-specific knowledge. Like I've said now, these models are already pre-trained with whatever information that was used, right? But in our case, at least, we're in a very scientific setting. So it could very well be the case there's a certain chemical or disease that's relevant to you and your project, and an LLM has no idea what it is. So you can fine tune the LLM with a lot of information about this chemical or disease to kind of fill in that knowledge gap that it didn't know about before. And same with Stable Diffusion. Let's say you ask it to generate you a picture of Spider-Man and it gives you back a spider wearing jeans. That's probably not what you were looking for, right? So you can do the same thing. You can go and scavenge for prompts with the word Spider-Man, get a bunch of images that correlate to these prompts and train, and just fill in the domain gap, fill in this knowledge, fill in those weights with this extra information that wasn't already there. The main advantage of fine-tuning as a whole is its efficiency. We're leveraging some already present knowledge and adapting it for a specific need, which saves us the time and resources from training from scratch. If you want to train from scratch, you need so much more data, and it's going to take so much longer. And if you're running this on things like RunPod, that's just going to raise costs a lot, right? And it's a lot more flexible. If anything goes wrong with fine-tuning and you don't like the way your outputs look, that's probably like a day or two of fine-tuning. You can stop, you can start again, create a new data set and go. If you're training from scratch, you're probably waiting maybe like a week for training to finish to actually generate something. If it doesn't look good, you have to curate so much more data and then start again, right? So it's a lot quicker. And for all the tasks that I've heard in the lab, at least, fine-tuning should be able to solve most of them. So let's assume everything's gone well now and you have a fine-tuned model. We're in a scientific setting. What's the next step? Evaluation. Evaluation is going to depend on your specific task, your specific use case, and what you want out of your model. So I'll just list a couple of metrics here. If you're working with LLMs, precision, recall, and F1, these are just going to give you different ratios of how correct is your model outputting things, right? So true positives, total positives, positive predictions, so all predictions and a mean of them. Zero Winkler is the measure of the string difference. So if you have two sets of strings, how much change you have to do to this to get this. Lose the measure of the quality of text generated. Sentiment analysis will tell you, okay, is this a positive tone of text? Is this negative? Maybe useful for a chatbot. LLM-based evaluation. Let's say you are creating a chatbot and your goal is for it to be helpful, maybe engaging, I don't know, kind. I don't know where to find metrics for these, but you could have a different LLM use these metrics to evaluate your specific chatbot. Maybe just save the outputs and give it to this additional LLM and have it give you back numbers. Human in the loop's a little bit more advanced of a reinforcement learning technique where an agent's going to train your model, a human's going to go in and score it. The agent will take the scoring and adjust the way it trains to help increase that score. Stable diffusion has similar ones. FID is the similarity measure between two images, so kind of like Gerald Winkler. Clip, remember, with stable diffusion and text to image, the goal is for the output image to closely represent the input text. So this is going to measure, okay, how closely do these two align? And PSNR, peak signal to noise ratio. Long story short, you can use it for things like how good is the quality of the image, how blurry is it, how clear is it, right? Things of that nature. And lastly, common issues. So everything seems fine and dandy. Yeah, you can fine tune, everything's going to be great, but there are things that you can run into. The first one's overfitting, so the models fit too closely to the training data and therefore has poor results in test data. This is the example I hinted at earlier, where if I keep telling you that red and blue is purple and I eventually ask you what is red plus yellow, you'll have no idea because all you know is red and blue is purple, right? You're kind of stuck and your knowledge is just stuck on what you've been seeing before. This is the purpose of having that validation set to make sure that the model's not getting overfit and is still good at generating outputs on information it's never seen before. For training data, we've talked a lot about numbers here, right? So it makes sense that the models are going to be sensitive to the data that you train it on. If your training data is not good, you can pretty much guarantee that the performance afterwards is not going to be good. You want to make sure you have enough examples and your examples are going to be relevant for the real world scenarios you're working in, right? So let's talk about research articles, for instance. If your training articles are things like this chemical comes from this and helps cure this disease, it's pretty easy to understand what this chemical is doing. But if your real data and the data that's going to be used on later on is something like this chemical, this inhibitor, this receptor, which leads to this percentage increase in this, it's a little bit more difficult. And if you've trained it on something so simple, the model's not going to be able to perform well on these more difficult articles, if that makes sense. Hyperparameter tuning may not necessarily be an issue, but just something you should be aware of. When it comes to fine tuning, there's a number of hyperparameters you can change, whether that's learning rate, warm-up steps, batch sizes, things like that. It's pretty much trial and error to figure out the best hyperparameters that work for your specific use case. Ideally, the default or whatever the community is using for that specific model should be good enough, but it never hurts to try and tweak them a little bit to see if you can get any better results. And catastrophic forgetting is a tendency of the model to forget what is learned prior to your training. So if I've trained a model on color combinations and then ask it a math question, it might not understand what that is, right? So it's kind of forgot all the general knowledge that I had beforehand before I told it all about these color combinations. Nonetheless, I think fine tuning is pretty cool. It's always great to see what you can do with fine tuning and creating these custom large language models, generative AI models, whatever it might be. And I am really looking forward to see what the lab has coming up in the near future. But otherwise, that's all for me, and I thank you for your time.